in this example, it's not so much of an example, it's to explain a phenomenon we've all experienced, certainly if you've been anywhere near water. And the question is, why do objects in the water appear closer than they really are? Okay? So let me repeat that. Why do objects, when they're in water, appear closer than they really are? So what we have here is, we have a very busy diagram. And so this happens to be the surface of the water. This would be air. This would be the surface of the water. This would be some pool, for instance. And let's say that the depth of the water here is represented by D. And so our D is equal to 1 meter deep. So let's say that you're at a pool. You happen to drop in a pair of goggles. I couldn't draw goggles, so I just wrote a G to represent goggles. But they're going to appear as though they're shallower than actually the one depth. They're going to appear that they're somewhere up here. And what is that depth at which they actually appear? Now, the index of refraction of water is going to be 1.33. All right. Now, what happens is that light from the goggles that gets reflected off the goggles is going to come up out of the surface, and then you're going to be able to see it. However, because of the index of refraction of the water, it's going to appear as though the goggles are not actually at 1 meter deep. They're going to appear as though they're actually shallower. If you've ever been swimming, for instance, snorkeling, and you're looking for something, you keep grabbing, but it's actually further away than it appears closer than it truly is. That's what we're going to be able to try to describe. So we have a body of water which is 1 meter in depth. We have a pair of goggles down at the bottom. Where do the goggles actually appear to be? All right. So this theta 1 is for where the goggles actually are. Theta 2 is the angle to the normal. Remember, the angles are always going to be measured to the normal of where they actually appear to be. All right, so we're going to work with a couple of triangles. One of the triangles is going to be represented by X, come down the normal to the goggles, and then back up to the surface. That's going to be one of the triangles. Another triangle we're going to be working with to solve this problem is going to be, once again, the same distance X, down the normal to where the goggles appear to be, and then back to the surface. And that's going to be represented by theta 2, Now, if we look at, let's just pick the large triangle, all right? So if we pick the large triangle, come down here, this is our theta, all right? Now the tangent of theta 1 is going to be equal to, remember, it's opposite over adjacent, right? So it's opposite. So this is going to be opposite, so that's going to be X over adjacent. If this is our theta 1, the adjacent is going to be this length of the normal, which is really D. So the tangent of theta 1 is going to be opposite over adjacent. This is going to be the hypotenuse. This would be the hypotenuse because we have a right angle there. And so if we're looking at the tangent of theta 1, that's going to be X over the adjacent, and the length of our adjacent is going to be D. Now for small angles, if we have small angles, so small theta, all right, then the tangent of theta 1 is going to be equal to X all upon D, which is going to be approximately equal to sine of theta 1. That's for small angles, if you have very small angles. Likewise, we can do the exact same thing for theta 2. We can say that the tangent of theta 2 is going to be equal to X all upon, now in this case it's going to be D prime. So here's our theta 2, this is going to be our X, then tangent, remember, is going to be opposite over adjacent, so this is going to be our adjacent because this is going to be the hypotenuse, and that distance is going to be D prime. Once again, because of the small angle approximation, this is going to be equal to the sine of theta 2, Now, remember, this is going to be the apparent depth, where it appears to be at. Now we can use Snell's law once again, so we'll use Snell's law. And what we have now, is we have n1 sine of theta 1 is equal to n2 sine of theta 2. Now, we can solve this by, we can rewrite this in such a way as that we have sine of theta 1 all over the sine of theta 2 is equal to n2 all upon n1. Now, but we can say that our sine of theta 1 is really x upon d, right? We just said that. We said if we have a small angle approximation, sine of theta 1 is going to be equal to x over d. So we have the x over d. Now here, sine of theta 2 is going to be equal to x upon d prime, x upon d prime. Now, our x's cancel, and what we end up getting is we have 1 over d all upon 1 over d prime, which is equal to d prime all upon d, all upon d. All right, sorry, I have to look at my notes real quick. All right, so that's what we have so far. All right, that's what we have so far. Now, we can write this in a fact of n2 upon n1 is equal to d prime, which is going to be the apparent depth, divided by the true depth d. Now, we know that n2, right? So n2 is going to be equal to 1. We know that n1 is equal to 1.33, right? 1.33. So therefore, we can solve this for d prime. So our d prime is going to be equal to d, and this is going to be n2 upon n1. We can now substitute, I'm kind of running out of room, sorry. I'm going to write it up here now. So we have, I'll use a different color, just so it stands out a little bit more. So we have d prime is equal to d, which is 1 meter, times n2 all upon n1. D prime is equal to 1 meter times n2 is going to be 1. N1 is 1.33. And so our d prime is equal to 1 divided by 1.33, which is equal to 0.75 meters. The units of meters still stays in. And what that tells us now, is that this goggle, the apparent depth of the goggle, is going to appear to be 0.75 meters as opposed to the 1 meter that it truly is. And the whole reason for this is because of due to the index of refraction. Remember, you're going to be standing up here. The index of refraction is going to be 1.0 because you're looking at it from air. And because of that change in index of refraction, it's going to bend so in this case, what's happening is the light is going from something more dense to something less dense. So the angle is going to be refracted further away from the normal than it would be if the light were shining from the light or from the air into the water. So that the refracted light is going to be further away from the normal, thus creating the effect that these goggles are much closer than they truly are. They're actually going to be 1 meter away, but the apparent depth from standing up here above the surface of the water is going to be that they are 3/4 of a meter deep as opposed to 1 meter deep.